Hello everyone, my name is Ankit Dongriyal. I am your mentor from Civil Engineering Department. I again welcome you on this YouTube platform of IMS GATE Academy. Dear students, as you all know, this is the particular high time when we should do our revision with a very effective manner, with a very smart manner, right? So for that particular thing, I am here so that today we are going to discuss about all the important formulas which will be discussed here for your foundation engineering, right? As you already know that Sandeep sir has already taken the session for your soil mechanics, where he has already covered most of the chapters. In today's session, I am going to take shallow foundation, pile foundation, soil exploration and stability of slopes, right? Yeah, hi Chandan. Yeah, hi Rakesh. Hi Guru. So by then just first share the session everyone, so that we can just start with our preparations. Yeah, good afternoon Chintu. Good afternoon everyone. I'm good Rakesh. I hope all your preparations are going good. Okay. So as we already know that in foundation engineering there are lots of formulas which we need to revise, right? So the concepts, everything we have already discussed in our GATE score booster session. This particular session, in this session we are not going to discuss as that of questions. In today's session, our main agenda will be to revise the formulas, right? To revise the concepts, that will be our mainly agenda. Yeah, thank you Chintu. So the first thing that we need to discuss is about what are the different types of foundations, right? So if I talk about the different type of foundations, can you tell me the different type of foundations? So we know that on the basis of the depth on which your foundation is going to transmit its load. As we know that foundation, we are constructing it for what? We are constructing it for so that our superstructure load can be transferred to the below soil, right? For that we need that substructure, which is nothing but foundation. So if this foundation, it is transmitting the superstructure load to the shallow depth, it will be known as shallow foundation. Whereas if the foundation is transmitting the load to deep foundations or deep soil, it will be known as deep foundation, right? So we classify foundation mainly as shallow foundation and deep foundation. Right? Now if we talk about the shallow foundation, mathematically how we can define this, that any particular foundation is shallow foundation? How we can define? On the basis of your depth to width ratio. Yes or no? So let's suppose this is the particular foundation, this is your column and this is the foundation, right? This is your ground level. Let's suppose this is your ground level. So we know that this particular depth, it is your depth of foundation, and this dimension of foundation, we call it as width of foundation. So if your depth of foundation by width of foundation, it is less than or equal to 1, you will call it a shallow foundation. This is according to one scientist known as Terzaghi. We all know that Terzaghi is nothing but the father of soil mechanics. So according to Terzaghi, if depth of foundation, it is less than or equal to the width of foundation, it will be a shallow foundation. Whereas oppositely we can say, if depth of foundation by width of foundation, it is greater than 1, it will be your deep foundation. Clear? There is another scientist who has given that if depth of foundation by width of foundation, it is less than or equal to 2.5, then we will say that the foundation is shallow foundation. and it is according to Scampton. It is according to Scampton, right? Whereas if we talk about the deep foundation, if df by b it is greater than 2.5, we call it as deep foundation. Clear? So this is the major classification which we should know. After that, we know that this particular foundation, it will be subjected to load. Due to that particular load, there will be generation of stresses. Now, how to calculate those stresses, you know already, right? In stresses in soil, in effective stress in soil, we study about how to calculate the stresses at any particular depth. Now, for the soil to take these stresses, it should have the sufficient strength. Yes or no? Our soil should have the strength to support this particular load, and this particular stress value or this particular supporting power of the soil, we call as that bearing capacity of soil. Clear? So mainly from this particular foundation part, examiner will ask you the question on the bearing capacity of foundation. So related to bearing capacity of foundation, we have different terms which should be known to you. Now there are different scientists, there are different researchers who has given their particular analysis for the calculation of bearing capacity, right? So we will see what are the different terms and how to calculate this bearing capacity value. Clear? Now, if we talk about the important terms, first term we have is gross pressure or gross pressure intensity, right? So what is this gross pressure intensity? Try to understand this. Let's suppose this is my particular foundation. This is your foundation. Right. And if we see at the foundation level, if we try to find out at foundation level, what are the different pressures? Let's suppose this is your particular foundation. This is the ground level. If we talk about what are the different pressure which are acting at this particular base of the foundation, what will be the different stresses? We can say that the stresses at this particular level, one will be due to this particular soil. Right? So the weight of soil will be there. One stress. Let's suppose this particular depth is depth of foundation. As this particular dimension, it will be very less as compared to this particular depth. Right? So we take that this particular depth is nothing but of soil. So I can say that this value will be, if this soil is having a gamma value, if this soil is having a unit weight as gamma, so I can say that due to this particular soil, the stress at this point will be gamma into df. Right? There may be some superstructure load as we are constructing the foundation. So obviously there will be some superstructure above that. Right? Due to this superstructure load, there will be some stresses at this particular point. Right? So there will be one stress due to this weight of the soil, we call it as overburden pressure. Overburden soil pressure. Right? Also, there will be stress due to this superstructure load. Plus stress due to this weight of the foundation. So these three components can cause the stresses at this particular point. Right? So the stress value due to these three factors, it will be your gross bearing capacity. Clear this thing? Now, so we mark this particular value with Q, or in some books you might find at QG. Sometimes we represent it with Qg also, right? So what is this Qg? Qg is the intensity of pressure at the base of foundation due to the load from the superstructure, self weight of the foundation and overburden. Clear? So due to these factors, there will be stress at the base of foundation. We are calling it as gross bearing capacity. Second term is our net pressure intensity. Net pressure intensity. Now what is this net pressure intensity? Now try to understand. If I talk about at this particular point stress value, before construction of our structure, this overburden pressure was there. Even before the construction of our structure, this particular soil was subjected by this particular overburden pressure. So the effective stress value due to our construction will be what? The effective stress value at this point due to our construction, it will be due to superstructure load plus weight of foundation. So if I only consider this particular net value, I am not considering this overburden pressure as it was acting even before the construction of our particular structure, right? So if I neglect this particular stress value, the stresses due to superstructure load and weight of the foundation, it will give me the net pressure value or net bearing capacity, right? So I can say if net pressure is Qn and gross pressure is Qg. So Qg is due to overburden pressure, superstructure load and weight of the foundation. If I subtract this gamma dF value, that is the stress due to this overburden pressure, what I will get? I will get the net pressure value. I will get the net pressure value, right? So here you can see net pressure intensity is the gross pressure intensity minus the overburden pressure, right? So it will be given as Qn is equal to Q minus gamma into dF, right? Now try to understand, this is the particular stress value which is acting at the base of foundation. Now this stress value can be greater than the strength of your soil also, right? Let's suppose your soil can only support 50 kilopascal of pressure, 50 kilopascal of pressure, and due to the weight of foundation, due to superstructure load, due to the weight of soil, you have applied 100 kilopascal of stress. You have applied the 100 kilopascal of stress. Now try to understand this. Let's suppose this particular stress value is 50 kilopascal. This stress value, the weight of the foundation, it is, let's suppose, 10 kilopascal, and this particular value is also 10 kilopascal. Just I am taking some random values, right? So what will be the total pressure at this point? Total pressure at this point, can I say it will be 50 plus 10 plus 10, that is nothing but 70 kilopascal. So this is my Q value or Q gross value. If I subtract this 10 value, that will be my net value. That will be 70 minus this 10 value. That will be 60 kilopascal. That will be 60 kilopascal. Now try to understand what is the ultimate bearing capacity of soil. Another term is ultimate bearing capacity of soil. Now ultimate bearing capacity of soil is the maximum value of gross pressure, is the maximum value of gross pressure which your soil can take, right? If you will apply the pressure value greater than this particular value, your particular soil is going to fail in the shear. Clear this thing? So if I suppose say the strength of this particular soil is 50 kilopascal. If I say the strength of this particular soil below this foundation is 50 kilopascal, can you tell me what is the maximum pressure value which can be applied on this foundation so that my soil below the foundation will be safe? Just tell me what will be the intensity of your pressure value such that my soil below the foundation will remain same. If the strength of soil is 50 kilopascal below this, just let me know. Rakesh, Chintu, just tell me. Chandan, what will be the stress value? Can I say that the maximum stress value which can be taken by this foundation, it will be 50 kilopascal only. If you'll apply the pressure value more than this particular value, your particular soil is going to fail, or ultimately foundation is going to fail. Yes or no? So this 50 kilopascal value, it will be my what? It will be my ultimate bearing capacity. It will be my ultimate bearing capacity. Clear? Now from this ultimate bearing capacity, again, if I subtract this particular weight of soil, or if I take the net stress value or net pressure value at which my soil below the foundation will remain safe, it will be your net ultimate bearing capacity. That will be QNU. So what will be QNU value? Ultimate value is 50. Overburden pressure is 10. So can I say it will be 40 kilopascal? Can I say it will be 40 kilopascal? Right? So this is what we have discussed. So ultimate bearing capacity, it is the minimum gross pressure intensity at which the soil at the base of the foundation will fail in the shear. You can write this particular definition in two ways. If you are talking about the failure, so this is the minimum gross pressure value at which your foundation will fail. Whereas if you take this particular definition from safety point of view, so it will be the maximum gross pressure value at which your foundation will be safe in shear, at which your foundation will remain safe in shear. I hope this particular concept is clear, right? Similarly, if you subtract from this gross pressure value or ultimate bearing capacity value, the weight of the soil above the base of the foundation, it will give you what? It is going to give you the net ultimate bearing capacity. It is going to give you the net ultimate bearing capacity. Clear? Now, these are the limiting values at which your soil is going to remain safe or your soil will fail, right? If you just apply the stress value above this particular ultimate bearing capacity, your soil will be fail in shear. Whereas, if you apply the stress value below just this particular value, your soil will remain safe, right? So, to be on the safer side, what we do? We apply the factor of safety on these particular values, right? So let's suppose, take an example. Let's suppose I have told you that my soil below this particular foundation will be safe at 50 kilopascal. So it is not like that you will apply the 50 kilopascal load on or pressure value on this particular foundation. Obviously, to take the factor of safety, what you will do? You will apply a stress value less than this particular value. You will definitely apply a stress value below this particular 40 kilopascal. Let's suppose you have only applied the stress value 25 kilopascal. You have assumed that, okay, this particular foundation can only take 25 kilopascal, whereas its strength was what? Its strength was, or ultimate bearing capacity was 50. It means you have applied a factor of safety of 2 on this particular value. What you have done? You have applied the factor of safety value of 2. Clear? So, if we apply the factor of safety value on these pressure values, we got safe bearing capacity value. We got the safe bearing capacity value. Now try to understand. Before the calculation of safe bearing capacity value, first we calculate the net safe bearing capacity. I will tell you that why we are doing that particular thing. So before calculating the safe bearing capacity, first we have to calculate the net safe bearing capacity. What will be net safe bearing capacity? It will nothing but the net ultimate bearing capacity divided by factor of safety. Divided by factor of safety. Now there is one common mistake which student used to do. What student do? When they are calculating the safe bearing capacity, they used to divide the ultimate bearing capacity with the factor of safety. With factor of safety. Clear? Now, what is the mistake in this particular form? If I just open it, it will be Q net plus gamma into df upon factor of safety. or you can write it as Q net upon factor of safety plus gamma df upon factor of safety. So the common mistake here is when we are directly dividing this ultimate bearing capacity with factor of safety, this gamma df term, which is nothing but the weight of soil above the foundation, you are also dividing it with factor of safety. Now, if the weight of foundation or the stress due to the if the stress due to the weight of this soil, if stress due to the weight of the soil, it is 10 kilopascal. It was 10 kilopascal even before the construction. It will remain 10 kilopascal even after the construction, right? You cannot change this particular value. It means you cannot apply the factor of safety on this particular value. This particular stress value, it was acting even before there was no construction. You can only change the weight of foundation, you can only change the load which you are applying over this particular foundation, right? So what we want, we don't want that the factor of safety should be applied on this particular weight of the soil, right? So for that, what we do, first we calculate the net safe bearing capacity and then we separately add the weight of soil which is above the foundation, So you can see that after calculating the net safe bearing capacity, we separately have added the weight of the soil above the foundation. That is nothing but gamma into depth of the foundation. I hope this particular concept is clear, right? If there is any doubt, just let me know. Now, if these terms are clear to you, examiner generally asks us for the safe load bearing capacity, safe bearing capacity, net safe bearing capacity, ultimate bearing capacity of soil and net ultimate bearing capacity of soil. So there are different researchers who has given their analysis for the calculation of this bearing capacity, right? So in this particular thing, the first name is Terzaghi. We also know him as a father of soil mechanics. So Terzaghi has given one relation for calculation of load bearing capacity. You will definitely get one question on this particular formula, that is CNC plus NQ into gamma into DF plus half gamma B N gamma. So here NC, NQ and N gamma, they are your Terzaghi bearing capacity factors and they are the function of your angle of internal friction. It means they are going to change with different phi values. Now for different phi values, what will be NC, NQ and N gamma? You don't need to remember these. These particular values will be given to you by the examiner. But for phi is equal to 0, it should be known to you. So for phi is equal to 0, your NC will be is equal to 5.7, NQ value, it will be 1 and N gamma value will be 0, right? Now this particular equation, it is only valid for strip footing. Also, it is only valid for shallow foundation. So there are different assumptions. So for shallow foundation it is valid. For strip footing it is valid, right? Also, in this particular formula, there is one major assumption that it is valid for general shear failure. Clear? So these three assumptions, it should be known to you that okay, it is valid for strip footing. So if strip footing is given to you, if general shear failure case is given to you, shallow foundation case is given to you, you can use this particular equation. Clear? One more assumption there is, in this particular equation, the water table is assumed below the influence zone of this particular foundation. It means here the effect of water table is not taken into account. So water table effect is not taken into account. Water table effect not taken. Right? So whenever these conditions will change, whenever the strip footing will change to square footing or circular footing or rectangular footing, this particular formula will also change. When this particular general shear failure will change to local shear failure, again this formula will change. If in case of, if there will be effect of water table, or if the water table, it will be, right? So just Let me know up to this particular point if there is any doubt. Up to this particular point, if there is any doubt, just let me know. क्लियर? तो याद रखना ये बात, अगर आपको जनरल शेयर फेलियर की जगह लोकल शेयर फेलियर दिया हो तो आपकी सी की वैल्यू, कोहेजन की वैल्यू, कोहेजन मोबिलाइज कोहेजन हो जाएगी, दैट विल बी 2/3 टाइम्स ऑफ सी. वेयरएज आपके पास जो मोबिलाइज फ्रिक्शन, एंगल ऑफ फ्रिक्शन होगा, इट विल ऑल्सो बी व्हाट, इट विल ऑल्सो बी phi m is equal to tan inverse 2/3. और इसको ऐसे भी समझ सकते हो, यू कैन ऑल्सो टेक इट एज tan phi m, it is equal to 2/3 times of tan phi. So where to use this particular tan phi m? This cm value will be used here, whereas this phi m value, now this nc, nq and gamma, you have to take this nc, nq and gamma value corresponding to this phi m value. As we have seen that these bearing capacity factors, they will be the function of phi value, right? So corresponding to this phi m value, now you have to take these values. I hope this is clear. Now there can be different changes. There can be different changes for the shape of the footing also. So if there is a square footing, remember our general formula was QF is equal to CNC plus QNQ plus half. I can write it as 0.5 gamma B and gamma. 0.5 gamma B and gamma, right? So for square footing, this particular value, this first term will be affected. In case of CNC, there is 1.3 CNC. This value is same, and in case of 0.5, you have to use 0.4 gamma B and gamma, right? Similarly, if there is a circular footing, this formula will change to 1.3 CNC plus Q and Q plus 0.3 gamma B and gamma. I have also given you the trick that remember it as like 0.5, 0.4, 0.3. 0.5, 0.4, 0.3. Clear? We know that this formula is for a strip. 0.4, remember it from 4. 4 is the square of 2. So this is for square footing. And this is for circular footing. The remaining will be for circular footing, right? If there is a rectangular footing, so in rectangular footing there will be two dimensions, one will be length, one will be width, right? So again this formula will be 1 plus 0.3 B by L CNC plus Q and Q plus 1 minus 0.2 B by L 0.5 gamma B and gamma. I have also given you the trick for this particular formula also. Remember that if B will be is equal to L, this particular rectangular foundation, it will nothing but a case of square footing. It will be a case of square footing, right? So try to see. We want here 1.3, right? So from here you can remember 1 plus 0.3, that will be 1.3 when B and L will be equal. So if you put B and L equal, it will be 1 plus 0.3, so it will be 1.3, right? So this particular term you can remember. Here we need 0.4. Here we need 0.4. It means we are already having 0.5 gamma B and gamma. If I multiply this particular value with 0.8, right, then I can get this 0.4. Then only I can get this particular 0.4, right? So it should make 0.8 value, right? So you can remember 1 minus 0.2, that is 0.8. When will be this case? When B and L are equal, right? So from here, if you somehow are not able to recognize the particular formula in the exam, or if you forget the formula, you can make this particular formula like this also, right? If you'll remember. I hope this is clear. Is this clear, Rakesh? So this is the major change due to the different shape of footing, right? There is another case where we have to take the effect of water table. There is another case of taking the effect of water table. Now we know that the zone of influence of any foundation, it lies up to the width of this particular footing below the base of the foundation. So from the base of the foundation, if you will move up to a depth equal to the width of foundation, up to this point only there is a zone of influence of this particular foundation. It means if there is any water table, it means if there is any water table below this particular level, it is not going to influence the bearing capacity of this soil or bearing capacity of this foundation. But if the water table will be somewhere here, so definitely there will be the variation in bearing capacity of foundation. Now how to take that bearing capacity of foundation changes into account, that we want to see. Now if I take that, let's suppose if I divide this particular into 3 zones, let's suppose up to this particular point, up from the ground to this depth of foundation, I am taking it as zone 1. From depth of foundation to width, I am taking it as zone 2. And here zone 3. So either water table will be in zone 1, either water table will be in zone 2, or water table can be in zone 3, right? So when water table is in zone 3, so this is the particular standard formula which has not taken into account the effect of water table. But let's suppose if water table is in zone 3, we know that there will be no change in the bearing capacity. So this formula will be valid. This formula will hold good for this zone 3, right, as there is no effect of water table. But let's suppose the water table is in zone number 2. Now try to understand this formula. This gamma into D, it represents the soil in this zone number 1. This gamma into D or gamma into DF I can take, right, as I have changed here a D value to DF. So this particular soil, the particular weight of this particular soil, it is represented by this term gamma into DF. Whereas the weight of this particular soil in zone number 2, that is gamma into B, it is taken into account by this term. Now you tell me, if water table is in this zone number 2, so my this weight of soil is going to get influenced. Yes or no, right? So let's suppose if I assume the water table is at a depth ZW2 from this base of the footing, right? So can I say, let's suppose if I take the unit weight of this soil to be gamma bulk, whereas this soil will be in the submerged condition, so gamma submerged, or we can also use gamma submerged as gamma dash. This is the symbol for gamma submerged. Yes or no? So here some part of soil is in bulk condition, some of the part of soil is in submerged condition. So what you can calculate? You can calculate a average value for this particular soil. You can calculate the average gamma value for this particular soil. So what will be gamma average? Your gamma average will be what? Your gamma average will be gamma bulk into ZW2 plus gamma submerged into B minus ZW2 divided by total thickness of this layer, that is B. Right? So here the gamma will be what? For this soil you have to take the gamma as gamma average. Here you have to take the gamma as gamma average. So for this particular, if water table is in zone number 2, so for zone 2, what will be my now new formula? It will be QF is equal to CNC plus, there will be no effect on this particular term as there is no water table in this zone, right? So this term will remain same, gamma into DF into NQ, but this term will get changed. It will be 0.5 into gamma. Now here the gamma is gamma average. Here the gamma is gamma average. Gamma B and gamma. I hope this is clear. I hope this particular concept is clear. Right? Now, let's suppose if water table is in zone number 1, if my water table is somewhere here in zone number 1, what will be the change? What will be the change? Now the change will be what? Again, if let's suppose water table is here. Water table is here. Now this particular soil in zone number 2, it is completely submerged. It means here the gamma will be now what? Here the gamma will be now gamma submerged. Yes or no? For this zone number 2, the whole soil is now in submerged condition if water table is in zone number 1. So, and for this zone number 1, now I have to take the average gamma. As this particular soil is, let's suppose this is in bulk condition and this particular soil is in submerged condition, we know. So here now the average gamma will be used, right? So what will be gamma average in this case? Gamma average will be gamma bulk into this depth, that is ZW1, plus gamma of this soil, that is gamma submerged, into this depth, that is total depth of foundation minus ZW1 divided by the total thickness of this layer, that is depth of foundation. Clear? So how my formula is going to change for this zone number 1? So for zone number 1, what will be the formula? For zone number 1, formula will be QF is equal to CNC plus, now instead of gamma there will be gamma average into DF into NQ plus half gamma. This soil will be now in submerged condition. Gamma submerged into B into N gamma. Gamma submerged into B into N gamma. I hope this effect of water table is clear to everyone. Just let me know. I hope this effect of water table is clear to everyone. Right? So how to take the effect of water table? Only there will be no change. There will be change in this due to this change in water table. The only change will be in this gamma value. So you have to see if water table is in zone number 2, this gamma is going to change. If water table is in zone number 1, this particular gamma will be completely gamma submerged and this gamma will be gamma average. I hope this concept is clear. Right? Now we can move to next topic. That is your Scampton's analysis. Right? Now, Scampton has given directly the value of net bearing capacity. So always remember this. According to Scampton, the net ultimate bearing capacity value is given. Whereas Terzaghi has given you the ultimate bearing capacity value. Right? So if net bearing capacity value, if it is asked according to Scampton, it is nothing but given by C into NC. It is given as C into NC, where NC is what? NC is your Scampton's bearing capacity factor. Again, depends upon the different depth of the foundations, right? So it depends upon the DF by B ratio. So you can see if DF by B ratio is less than or equal to 2.5, it means according to Scampton, this is the shallow foundation. If DF by B is greater than 2.5, it means this is our deep foundation. So if footing is strip footing, for shallow foundation, it will be 5 into 1 plus 0.2 DF by B. All these are the values of your NC. NC is your cohesion value, right? So these are the values of NC. Whereas for deep foundation, it is independent of depth of foundation and width of foundation, it will be 9.5. For square and circular footing, this value, it will be 6. This factor will be 6. The value will remain same. 1 plus 0.2 DF by B. Again for raft or rectangular footing, it will have two dimension, width of foundation and length of foundation. So you can see here there are two particular dimensions. So it is 5 times of 1 plus 0.2 df by b into 1 plus 0.2 times of b by l, right? And for D foundation, they are independent of these dimensions. So it is 9.5 for strip footing, for square footing it is 9, for raft footing also it is 9. Clear? If df by b is equal to 0, if df by b value will be equal to 0, it is nothing but the special case of shallow footing only, right? If df by b is equal to 0, it means your df by b is less than equal to 2.5. So your NC value in this case, it will be 5, this ratio becomes 0. For square and circular footing it will be 6, as this particular value generally asked. So I have given you the separately these values also. Clear? So I hope up to this particular point it is clear. So you need to remember these formulas of NC value, right? Sometimes they can ask for this particular value. Always remember here this particular value is net ultimate bearing capacity. What student do? If sometimes it is asked to calculate the net ultimate bearing capacity based on Skempton analysis, they calculate this CNC value and they subtract gamma df value also, right? So always remember this is directly the net ultimate bearing capacity. This particular analysis of Skempton, it is also valid for shallow and deep foundations, right? It is valid for both shallow and deep foundation, right? Shallow and deep foundation. Also, this particular analysis, it is only valid for cohesive soils. You can see the cohesion value. So it is only valid for cohesive soil, not valid for cohesionless soil. Clear? Up to this point, just let me know if there is any doubt. Just let me know if there is any doubt. Next, if we revise this Meyerhoff's theory, right? So Meyerhoff has taken into account the shape of foundation, depth of foundation and inclination of foundation by these factors, that is SC, DC, IC, SQ, DQ, IQ and S gamma, D gamma, I gamma. Here S, they are your shape factors. These are your shape factors. D values are your depth factors and I is your inclination factor. I value is your inclination factor, right? Based on this Meyerhoff analysis, sometimes they can ask you question on the eccentric loading. So this particular analysis also taken into account the eccentric loading. So let's suppose this is the particular foundation. It is having a eccentric loading. Let's suppose the eccentricity is E only in one direction. Let's suppose in x direction Ex, right? Let's suppose this is the width of foundation B. So here to take into account this eccentricity, we use this effective width. How to take into account? We use the effective width B dash, and that B dash will be B minus 2 times of this eccentricity. Clear? So if eccentric loading is given to you, instead of this B, we have to use this effective dimension, right? So this effective dimension, it will be used here. Also, if the load carrying capacity is asked to you, all these formulas are for the bearing capacity. If load carrying capacity is asked to you, you should know that these are the value of stresses or pressure. If you will apply these, if you will multiply these pressure value with the area of base of foundation, then you are going to get the load carrying capacity of that particular foundation, right? So always remember these are the pressure values. To calculate the load carrying capacity, you have to multiply this particular stress value or pressure value with this area of the foundation. So when you are taking into account the area of foundation, instead of this dimension B, you have to take into account this B dash value. Clear? So sometimes this questions on the eccentricity may be asked, so you can tackle that question in this particular manner, right? Okay. in this chapter, the next important part is the calculation of load bearing capacity based on your in situ test. So there are different type of in situ test based on which you can calculate the bearing capacity of soil, right? So this is the particular setup for your plate load test. This plate load test, originally it was discovered for the calculation of your modulus of subgrade reaction, which you use in the highway engineering, right? So what is this particular test? Just try to understand it first. Let's suppose this is the particular field. You want the bearing capacity of this particular foundation, right? You want the bearing capacity of this particular soil. Now, to get the bearing capacity of soil, what is that ultimate bearing capacity of soil? It is the minimum value of pressure, or it is the minimum value of gross pressure at which your soil will fail in shear. It means to get that particular minimum value, you have to fail this soil. You have to apply the load on this particular soil up to the failure. Now for that, a very heavy load will be required. Also your soil at this particular level will get fail. So what we do this particular analysis. We do this particular analysis on a plate, right? So let's suppose this is that ground. So to analyze this particular condition, what we do? First, we excavate the soil up to the original depth of foundation. Always remember, this test, it is conducted at the original depth of foundation at which you are going to construct your depth of foundation, right? So this depth of excavation, it will be equal to depth of foundation, and to avoid the contraction from the sides, you take this particular dimension. Let's suppose this is the width of excavation, and it should not be less than 5 times the width of plate which you are using. So mainly what you are doing, instead of foundation, you are assuming that this is my particular foundation. We use one plate here. So this plate can be circular or it can be a square plate. So this is your plate having dimension BP. Now on this particular small area, you are going to apply the load. Due to this application of load, what will happen? Due to the application of load, you will find out that this particular plate, it will get settled. This particular plate will get settled, and one particular stress value, your soil is going to get failed, right? So to analyze the result, what you do? We mainly construct a load versus settlement curve. We mainly construct the load versus settlement curve, right? So you are keep on applying the load over this particular plate. So what will happen? As you are increasing the load, there will be settlement in this particular plate at particular load value. When the stresses over this soil, will be greater than the strength of the soil, what will happen? Your soil is going to fail in shear, right? And the corresponding load value, you can note down. If you will divide this load value with this area of the plate, you will get the ultimate bearing capacity. Of soil, but corresponding to plate. Right? I am calling it as QUP. So we got the ultimate bearing capacity corresponding to plate. What we want? We want the ultimate bearing capacity of this foundation, not of plate, right? So for that, we are having different relations based on the different type of soil. So you can remember, if the soil is clay soil, so in clay soil, always remember in cohesive soil, in clay soil, your load carrying capacity or bearing capacity of soil, your bearing capacity of soil, it is independent of the size of the footing. It is independent of the size of the footing. So whatever is the bearing capacity for a small plate, same will be the bearing capacity for total foundation. It means it is independent of the size, right? So in case of clay soil, your ultimate bearing capacity of foundation, it will be same as ultimate bearing capacity of plate. Clear? This is case number 1. Whereas in case of your sandy soil or cohesionless soil, in case of cohesionless soil, your ultimate load carrying bearing capacity of soil corresponding to foundation to ultimate bearing capacity of soil corresponding to plate, it will be directly proportional to its dimension. So width of foundation by width of plate. Width of foundation by width of plate. Clear? This is for the shear failure criteria. When your foundation is getting fail under shear, so shear failure criteria. It may also be possible that when you are applying the load over a plate or stresses over particular soil, there may be a settlement value which may be greater than the permissible value suggested by the IS code. If the settlement value in the foundation, it is more than the permissible value given by the IS code, you will say that your foundation is fail under settlement criteria, right? For the settlement criteria also, when we got the settlement failure for the plate, based on that you can calculate what will be the settlement in your foundation, right? So based on settlement criteria, based on settlement criteria. So based on settlement criteria, first in case of clay, in case of clay soil, so your settlement of foundation to the settlement of plate, it will be equal to width of foundation to width of plate. It will be width of foundation to width of plate, right? Same as if we talk about for sandy soil or cohesionless soil, your settlement of foundation to settlement of plate, it is given as width of foundation to width of plate multiply by width of plate plus 0.3 upon width of foundation plus 0.3 whole square, right? Now always remember, while using this particular formula, there is one particular factor, right? That is 0.3. So this 0.3 you can use only when the width of foundation and width of plate are used in meters. So always remember, in this particular formula, the width of foundation and width of plate, they should be used in meters. They should be used in meters. I hope this concept is clear, right? So you have to use the width of foundation and width of plate in meters, then only this particular formula will be valid, right? So this is all about your plate load test, right? There is another test, in situ test, for the calculation of bearing capacity of soil, that is your SPT test or standard penetration test. Now try to understand first that what we are doing in this SPT test. In this SPT test, there is a split spoon sampler. So we insert this split spoon sampler after making some borehole, right? So this particular test, it can be done at different depth. This particular test also used for soil exploration. So if you want to explore the soil at different depth, so you can perform this test for the different depths, right? So what we do, we particularly make one borehole. So we have made one borehole. In this borehole, we will insert our split spoon sampler. So you can see that one sampler is inserted in it. Now over this sampler, we apply the dynamic loading by making the free fall of a load, by making the free fall of this particular load, right? Now this load or this hammer, it is having a weight is equal to 63.5 kg, and the height of hammer from which you are falling this particular weight, that is 75 centimeter. That is 75 centimeter, right? Now what we do, when we will apply this particular impact of hammer on this particular split spoon sampler, there will be penetration of this sampler, right? So what we calculate the number of blows required for 150 mm of penetration. So what you will do, you are keep on applying the impact load over this particular split spoon sampler. Due to this impact load, this sampler will get penetrated into the ground. So what you do, you will count that, okay, when my penetration reaches to 150 mm, for that how many number of blows are required. So here there is number of blows. Let's suppose they are N1. Let's suppose those number of blows are N1. This test, it is continued for again next 150 mm penetration. So we'll keep on applying the number of blows. Let's suppose for next 150 mm penetration, the number of blows are required is N2, right? Again, this test, it is conducted up to 450 mm of total penetration. So again there will be one more 150 mm penetration. You will also count that what are the number of blows required for this penetration, right? Now your SPT value is taken as the number of blows required for last 300 mm penetration. Your number of blows required for last 300 mm penetration. It means your N value, now we call it as an observed value. This is the N value you have observed, right? So this N value is taken as the number of penetration required for last 300 mm of penetration. Last 300 mm of penetration, that is N2 plus N3. That is N2 plus N3. I hope this is clear, right? Now we are calling it as observed N value. It means there will be error in this particular test. So for that we have to apply the different corrections. So on this observed value, we mainly apply two type of correction. One is your overburden correction and second is your dilatancy correction. Now try to see why we are applying the overburden correction. If you might have observed, when you want to penetrate, let's suppose you want to penetrate this particular stump, cricket stump in the ground. So what will happen? Initially when you will try to penetrate this stump into the ground, it will easily get penetrated. But at the greater depth, you have to apply the more power or more impact so that this particular stump will get penetrated into the ground. It means initially this particular split spoon sampler, it will get easily penetrated. But at a greater depth, what will happen? At a greater depth, there will be one soil. There will be the soil inside of this particular sampler, which will apply a overburden pressure over this. Due to that, its penetration will decrease, right? So what we can do, that at a smaller depth we will get a higher N value, whereas at a smaller depth we will get lower N value. Clear? Or you can also say at a smaller depth, we will get, yes, we will get less number of N values for same penetration. For same penetration, you will apply less number of blows. Whereas at a greater depth, for the same penetration, you have to apply more number of blows. Yes or no? It means here the n value will be more. Clear? It means at shallow depth, your n value is underestimated. It is underestimated. Whereas at greater depth, your n value is overestimated. Why it is overestimated? At a greater depth, there is more overburden pressure. So to take into account that overburden pressure, we apply the overburden correction, right? So what will be the overburden correction value? What will be that overburden correction value? So let's suppose this N1. So for overburden correction, so after applying the overburden correction, this is your N corrected. This is your N1 is your N corrected. So your N1 is going to be equal to N naught upon N naught into 350 upon sigma naught bar plus 70. Sigma naught bar plus 70. Now try to remember that this particular factor, this is the correction for your overburden. This is the correction for overburden. This correction factor should not be less than, this correction factor should not be less than your, this, if I say this is the correction factor, it should not be less than one value. It should not be less than one value. It means this stress value, it should not be greater than your 350 minus 70. Right? It means $280 value. It means 280 value. Clear? I hope this concept is clear. So N corrected for overburden correction will be N naught into 350 upon sigma bar plus 70. Right? Also, there is more correction, that is water table correction, or we also call it as dilatancy correction. So you can say it as water table correction. Water table correction. If let's suppose at test level or above the test level there is water table, so definitely the number of blows required for the penetration, it is going to change due to this effect of water table. So for that you have to apply the water table correction factor, right? So what will be water table correction factor? Always remember, after applying the overburden pressure correction, you apply this water table correction, right? So they are applied in this sequence. First you have to apply the overburden correction, then you have to apply the water table correction factor. So N corrected, that is N2 is also N corrected for water table correction. So N2 will be equal to, you will apply this water table correction on this N1 value, right? N1 plus half of N1 plus 50. This will be a correction for water table, that is N2 value, right? Just let me know up to this particular point if there is any doubt. Up to this particular point, if there is any doubt, just let me know. Right? N1 plus half of N1. Okay, this will be minus, sorry. N1 minus 50. Clear? Just let me know up to this point if there is any doubt. Rakesh, you remember all these formulas? Just let me know if there is any doubt up to this particular point. Is there any doubt? Okay. So we'll just proceed. Next is our pile foundation. Next is our pile foundation. Now try to understand. In pile foundation, we are generally asked for the calculation of load carrying capacity of pile. How much load your pile can carry, that examiner will ask you to calculate, right? So based on the load carrying capacity, there are different types of pile. So try to understand first. Let's suppose this is a pile foundation. This is your pile foundation. So when you are applying the load from the superstructure, this load, it will be supported by one at the ends due to this bearing. So we call it as end bearing resistance. End bearing resistance. When you are applying the load over this particular pile, this pile will try to settle down. This pile will try to settle down. So this pile will move down with respect to the surrounding soil. When this pile will have a relative motion with respect to the surrounding soil, what will happen? There will be generation of friction on the side. There will be generation of friction on the side. Yes or no? And this friction will be in the opposite direction to the motion. So there will be one resistance applied by this friction. We call it as side friction resistance. We call it as side friction resistance. It means the load carrying capacity of your pile, it will be due to, one is end bearing resistance, second is side friction resistance. Clear? So if your pile is supporting the load due to this end bearing and side friction, we call it as end bearing plus side friction pile. Clear? Whereas there can be some case when there will be no end bearing resistance, or there can be some cases when there will be no side friction. What can be the different cases? Let's suppose there is one pile which is standing over a hard strata. Let's suppose this is a rock. Clear? Now if we will apply the load over this particular pile, what will happen? It will support this load due to this end bearing. Now this pile cannot settle with respect to this particular soil. There will be no movement of this pile corresponding to or with respect to the surrounding soil. It means there will be no generation of side friction. So in such type of cases, you will only get end bearing resistance. You will only get end bearing resistance. Clear? Also there can be some soil. There can be some case. Let's suppose this is one pile and this soil is very loose soil. This is very loose soil. So what will happen in this particular loose soil? There will be some end bearing resistance, but its value will be very less, right? There may be the end bearing resistance, but its value will be very less as compared to the side friction. So in that case, we generally neglect this end bearing, and it means in these type of pile, there will be only side friction resistance. There will be only side friction resistance. Only side friction resistance. Clear? So based on the criteria that how they are distributing the load or how they are carrying the load, we can classify pile as friction pile, we can classify pile as end bearing pile, or end bearing plus friction pile, right? Now we need to calculate how to calculate the load carrying capacity of this friction pile, how to calculate the load carrying capacity of end bearing pile, how to calculate the load bearing capacity of this end bearing and friction pile. So we will take this particular case and we will see that how to calculate this particular value, how to calculate this value, right? So separately, if these values are known to me, I can calculate this only end bearing resistance for this case and the side friction resistance for the second case, right? Now try to understand. Let's suppose this is the particular pile, right? So we generally take into account two types of pile, one which is having a circular base area and second is which is having a square base area, right? So these two types of cases generally asked to us. So we can see that the load carrying capacity of pile, we will take a term as QUP. This load carrying capacity of pile, it will be resisted by this end bearing resistance, that is QEB, and side friction resistance Now how to calculate these values? Again, these values will depend upon the type of soil also, right? So in cohesionless soil, we can say that load carrying capacity of pile, it will be equal to end bearing resistance. Now these are the value of resistance. If you multiply this value with area, then you will get the load value. So this is the end bearing resistance multiply by, this is acting at this base area, so multiply by area at base plus side friction resistance multiply by area at side. Clear? Now how to calculate this QEB? This QEB, it is calculated by Skempton's formula. If you remember Skempton's formula, that is CNC, right? For circular or square values, that NC value was 9. That NC value was 9 for deep foundation. As we are dealing with deep foundation, so we know by Skempton's formula, Q net ultimate, it was CNC and this NC value for deep foundation was 9. So it is nothing but case of 9C. So this QEB value is nothing but equal to 9C into area at base plus QSF. QSF is your what? QSF is side friction. This side friction will be due to the interaction between this pile material and soil material. So this green color, it is your soil material. This red color, it is your pile material. So there is a force of attraction between this pile material and this soil material, right? So due to that, it is a case of cohesive soils. Later on we will discuss about the cohesionless, right? So this is the case of, just pardon me, this is the case of your cohesive soil, as we are taking into account the cohesion, right? So there is cohesion between these two particles, force of attraction between these two particles, as they are unlike particles. This is the pile material, this is soil. It means here the effect will not be the cohesion but adhesion, right? So to take into account that adhesion, we multiply this cohesion value with one factor known as adhesion factor. So that will be alpha into C. Now you know that along this particular length, your cohesion value may change. So we take the average cohesion value. So this QSF will nothing but alpha into C bar and this AS. Right? So this is the load carrying capacity of pile in your cohesive soil. Right? Skempton is used for cohesive soils only. So this particular case is for your cohesive soil. Similarly, we can derive the relation for cohesionless soil. Now, again QUP will be is equal to what? It will be QEB into area at base plus QSF into area at sides. Yes or no? Now this QEB is calculated by Meyerhof theory. We know that according to Meyerhof's theory, the bearing capacity, it will be given as CNC plus QNQ, or you can write it as gamma DF NQ plus gamma into DF into NQ plus half gamma B N gamma. As it is the case of cohesionless soil, this term will be 0, right? As you know that the depth of foundation in pile foundation, it is very much greater than the width of the foundation. This is the width of foundation, this is the depth of foundation. As this depth of foundation is high as compared to this width of foundation, or you can say this width of foundation is very less as compared to this depth of foundation. So this term also we neglect. We also neglect this term. So our ultimate bearing capacity will be gamma into DF into NQ. So it will be equal to QEB will be gamma into DF. Now depth of foundation in pile foundation is nothing but equal to the length of foundation. So it is gamma into L into NQ into AB plus the side friction resistance. In this particular pile, the friction will be from the sides, right? Now we know that friction, it will be is equal to mu into normal force, or stress value if I take, it will be is equal to mu into sigma, right? Or normal stress value. If I am taking this particular surface, the normal for this will be this. The normal stress value will be this. Yes or no? Or normal force will be this, right? Now try to understand. Try to understand. This will be the normal force. Now how to calculate this normal force? We know that this normal force, or this particular force value, it will be is equal to the earth pressure force that is given by, or this pressure value will be what? If I just assume at this particular point, it will be 0 here, it will be K into gamma into this Z, right? Or if I calculate it for complete soil, it will be K into gamma into L, right? So we know that at different point, the stress value is different. So what we do, we take the average of this stress. We take the average of this stress, right? So it will be, or you can say the area of this particular value, it will give you the normal force. So its value will be half K into gamma into L, that is the average value, into this is the normal stress value, multiply by mu value, that is 10 delta. That is 10 delta. Mu is what? Mu is the friction coefficient between these, and which is nothing but equal to 10 times the angle of friction. 10 times the angle of friction, as if it would be the interaction of soil to soil or pile to soil, this delta value, it could be the angle of internal friction of soil. But here, as there is interaction between pile material and soil, so you have to take into account the angle of friction between these two materials, right? So what is this delta? Delta is the friction angle between pile and soil material. Clear? This is the stress value into AS. Into AS. So this is your load carrying capacity of pile. This is the ultimate load carrying capacity of your pile. I hope this particular concept is also clear. Now try to understand how to calculate this AB and AS value. How to calculate this AB and AS value. Now try to see here. Generally, two types of foundation are given to you. One which is having a circular base, and second which is having a square base. So in this case, if I calculate the area at base, so what will be area at base? Area at base will be the area of this circle. Let's suppose it is having a diameter d, so it will be pi by 4 into d square. And what will be side area? It will be the curved surface area, that is area of this, or circumference of this multiplied by this length, that is pi into d into this length, that is the side area, right? Whereas if square pile is given to me, or the pile with having a square base is given to me. How to calculate? We can calculate that area at base will be what? Area at base will be the area of this square. If this dimension is b, so can I say it will be b square, that is b into b, that is b square, and area at sides will be the parameter of this multiplied by the length. So parameter will be 4 times of b into L. 4 times of b into L, right? So this is 4 times of b, this is your b, this is b, this is b, this is b, multiply by the length of the pile. It will give you what? It is going to give you area at sides, right? So these values you need to remember: 9c, alpha c bar, gamma L NQ, half k gamma L into 10 delta, right? From where we got these values, this is also now known to you. Clear? Now, there are some dynamic formulas also which should be known to you. So we know that there is one engineer's new record formula, that is ENR formula. So there are some empirical relations also, that is ENR formula, that is engineer's new record formula. So this particular formula, it was published in this particular paper or this magazine, that is engineer's new record. So we call this particular formula as engineer's new record formula only, right? So this is your ENR formula. According to this, the safe load carrying capacity of pile, it is equal to weight of hammer into height of fall of hammer given by factor of safety into S plus C. S plus C. Now try to remember, this W is nothing but weight of hammer. We are calling it as dynamic method. So again in this, we apply the different blows through the hammer from a particular height, and we got this particular W into H as energy. We are comparing this energy with the work done, that is the load carrying capacity multiplied by the settlement value, right? So this energy we have equated it with the work done. From that we got this relation. So what is this W? This is the weight of hammer. This H, it is your height of fall. Clear? Now remember, this safe load carrying capacity, it will have a unit of weight only. So whatever is the unit of this W, same will be the unit of this. Same will be the unit of this. And this height of fall and this unit should get cancelled out. This height of fall and this unit should get cancelled out. It means this will also have a unit of length and this will also have a unit of length. Now try to remember, this C value, it is your constant. This is your empirical constant having a value as 2.5 for drop hammer, and 0.25. These values are in centimeters for stream hammer. As these C value is in centimeter, all other length values we have to take into centimeters only, right? So always use this particular height of fall also in centimeters. This S value, we call it as set value. This set is nothing but it is the penetration per blow. This is the penetration per blow. And this penetration value, this S value, it is measured for, S value is measured for last 5, average of last 5 number of blows. S is calculated as average of last 5 number of blows. So in last 5 number of blows, what is the average penetration? That will be your set value. In case of drop hammer. In case of drop hammer. Whereas this S value, it will be the average of last 20 number of blows. Last 20 number of blows in case of steam hammer. In case of steam hammer. this factor of safety, if it is not given, so in this particular equation, you can take this factor of safety as 6. You can take this factor of safety as 6. So all these values should be known to you. What is this S value? That is set. So this set also you have to take in centimeter. This C constant, we know it in centimeter only. For drop hammer, you have to remember this as it is 2.5 centimeter. And for steam hammer, it is 0.25 centimeter. Clear? Always remember, if examiner will give you directly the 5 number of blows S value or penetration value, you should take the average of last 5 number of blows to calculate it in the case of drop hammer, whereas to calculate the S value, that is set value, in case of steam hammer, you have to take the average penetration of last 20 number of blows. I hope this particular concept is clear. So this is your dynamic method. Similar method, as in this method, the efficiency of hammer and efficiency of blows is not taken into account. This phenomena is taken into account by Hille. We know as it as Hille's formula. So it is based on also same concept. The only change is here efficiency of hammer and efficiency of blows is taken into account. Efficiency of hammer and efficiency of blow is taken into account, as we know that it is not necessary that this particular blow by the hammer, it will be having the impact of 100%, right? So if the impact is 100%, you will say, okay, efficiency of blow is 100%, that this particular value will remain 1. Also, this efficiency of hammer, so the hammer efficiency, as it is the mechanical equipment, so this efficiency of this hammer may also change with time, right? So if we are taking into account the efficiency of hammer and efficiency of blow, so this will be the particular formula. So W into H, efficiency of hammer into efficiency of blow, divided by factor of safety into S plus C by 2. Remember, here the factor is C by 2. Clear? So all these values are mentioned here. If these efficiency of hammer and blows are not taken, you can take it as 100% also, right? Also, you can remember that for the double acting hammer, you can remember these 2 points. For double acting hammer, this efficiency of hammer is taken as 65%, and for drop hammer, it is taken as 100%. In case of absence of data, you can use these values. Otherwise, you can take it as 100% if the values are not given. Clear? Next important concept is your group action of pile. We know that we never use a single pile for our foundation. There will be number of piles or groups of pile. Now, the total load carrying capacity of a single pile, and if you multiply that particular load carrying capacity with total number of pile, it may not be equal to, or you will not get the same load carrying capacity when you are calculating, when you are taking all the pile as a single unit and calculating the load carrying capacity. As we know, then when the spacing between these pile, will be less, so what will happen? The influence zone of these pile will get overlapped. So definitely there will be a different value of load carrying capacity of a group pile as compared to when you are taking all the piles individually and adding their load carrying capacity. Clear? So let's suppose when you are calculating the load carrying capacity of a single pile, it is QUP. Clear? And for now I am taking the total number of pile are n. Total number of pile in this group are n. Total number of pile equal to n. So when you are taking each pile as an individual pile, so the total load carrying capacity will be what? Total load carrying capacity of group will be what? It will be n times QUP. How to calculate this QUP value? It is now known to us, right? We have seen the different methods. We have seen the formula for end bearing pile. We have seen the formula for friction pile and the combined pile, right? So this will be n into number of pile multiplied by the load carrying capacity of a single pile. Clear? Whereas if we are taking all the pile as a one unit, so there will be different load carrying capacity. So let's suppose that load carrying capacity is QUG, total load carrying capacity. Total load carrying capacity. It is equal to QUG. When you are taking all the pile as a single unit. So this is also the load carrying capacity of group. This is also the load carrying capacity of group. So out of this, which value you have to take as a load carrying capacity of this complete group? It will be what? It will be the minimum value of out of these two. It will be the minimum value of these two, right? So what will be our load carrying capacity of a pile group? So load carrying capacity of pile group, let's say call it as QG. It will be minimum of ultimate load carrying capacity of a group when they are taken as single unit. When group is taken as single unit, or you can also call it as group action. And n times of when you are taking it as individual pile or individual action. Minimum of these two values, it will be our ultimate load carrying capacity of pile group. Yes or no? Clear? So this QUP value we know how to calculate. The problem is with this QUG value. Now we want to see that how to calculate this QUG value. Now always remember that this group action of pile or this group of pile, it is constructed in a square pattern. It is always constructed in a square pattern. So let's suppose there are two pile in a row. So there will be two columns also, right? So this is one square pattern. This is what? Our square pattern, right? This is the top view. This is the top view of your pile foundation. So there are 4 number of pile. Similarly, if let's suppose in a row there are 3 pile, so definitely there will be 3 columns also. Definitely there will be 3 columns also. So this is what we are saying, that the pile group, it is made in a square fashion. It is made in a square fashion, right? So let's suppose there are different pile. So this is one pile, second pile, third pile. So let's suppose this is my pile foundation. All the pile are having a same size. Clear? So all these are your pile. So can I say that the combination of all these pile as a single unit, it will act as a pile having a square dimension of this B? Having a square dimension of this B, right? Now how to calculate this width of the complete pile? Let's suppose the diameter of a single pile is D. The diameter of single pile is D, and center to center spacing between the pile is S. Center to center spacing between the pile is S. So this is S, this is also S. Clear? This is D, and this is D by 2, as total diameter is D. So this will be D by 2, here it will be D by 2. Clear? So what will be this B value? In this case, this B value will be what? It will be 2S plus D. This is when our pile is having 3 number of pile in a row, right? So if I make it generalized, what I can say, if let's suppose there are n number of pile, if there are m number of pile in a row, so if I say if m number of pile in a row, so what will be my V value? It will be m minus 1 into S plus D, m minus 1 into S plus D, yes or no? Clear? So it will be m minus 1 into S plus D. Once you know this particular width value, it means the dimension of this pile group as a single unit is known to you. Now you can apply the formulas which are known to us for that single pile, right? And there with the slight change. Now we'll see what will be the changes. So in case of sand, if I need to calculate this QUG value, so QUG value for a single pile we know that it is 9 CAB plus, now try to understand this green color, it is my soil, this is particularly also soil. So here you can see that in group action, the interaction here, the interaction at sides, it is mainly in between soil and soil particle. It is mainly in between soil and soil particle, as this is total a soil. So there is very small interaction between pile and soil material. Most of the interaction is between soil and soil. If there is interaction between soil and soil, that is like particles, so instead of adhesion there will be only cohesion, right? So what I can say, there will be only cohesion, or I can say it will be alpha into C bar into AS, as it is cohesion only, so I can say this alpha value will be 1. In this case, alpha value should be equal to 1. Clear? Similarly, in case of clay, always I am taking it wrong. It is for clay. For sand, if I write, so what will be the formula? QUG will be is equal to what? QUG value, we know it is NQ into gamma into L into AB plus half K gamma into L into 10. Here now the interaction is between soil and soil. It means the angle of friction will now be generated in between soil and soil particle, and we know that in between soil and soil particle the angle of friction is known as angle of internal friction, that is phi. So it will be 10 phi into AS. So this will be your QEG value. This will be your QEG value. I hope this concept is clear. So the only change will be, now here as the interaction is between soil and soil, so instead of alpha, their alpha value will be now equal to 1, and your delta value will be now equal to phi. So here delta is equal to now phi and alpha value is equal to 1. This will be the only change. Other than that, you can just assume it as a square pile or a pile having a square base. Clear? How to calculate the area now? We know that area at base, it will be what? It will be B square, and area at sides will be what? It will be 4B into L. Clear? How to calculate B? That we have also seen. How to calculate the B value? That is also now known to us. Clear this thing? Next is, sometime it can ask you for the efficiency of group efficiency of pile. So group efficiency of pile is nothing but it is the ratio of the ultimate load carrying capacity of a pile group when we are taking all the group as a single unit or all the pile as a single unit, right, or in a group action, whereas divided by total load carrying capacity of a pile group when you are taking it as an individual action, right. So it is the ratio of QUG to n times of load carrying capacity of an individual pile, right. There is one empirical relation also known as Converse-Lebare formula. So according to Converse-Lebare formula, your efficiency of pile group, it is 1 minus theta by 90 into m into n minus 1. I will write it again for you if it is not visible here. So efficiency of group pile, it is 1 minus theta by 90 m into n minus 1 plus n into m minus 1 upon m into n. What are these m and n value? Let's suppose this is your group of pile. Clear? Let's suppose this is the group of pile. So number of rows, this is your m value. So there are m is equal to 3 in this particular case, number of rows, and n is your number of columns. That is, n is equal to, in this case, is 3. What is this theta value? This theta value, it is the angle made by one pile with this second pile. Clear? So you know that this is particularly d value. This is your spacing between the pile, s. So if I take this angle is your theta value. So I can take it as tan theta is equal to what? Tan theta is equal to d by s, that is perpendicular by base. So theta will be tan inverse of d by s. Tan inverse of d by s. I hope this is also clear. So last year they have asked the question from this particular formula. At that time the formula was also given to you. What is the theta value also given to you. But as this particular topic, it is added in 2021 only. So that time they have given the particular formula. But now onwards it may be possible that they will ask this directly. Right? Also, as group action is added in your syllabus, so there may be chances that they can ask a question on group settlement ratio also. Group settlement ratio also. So it is nothing but it is the settlement of a group to the ratio of settlement of individual pile, which is given by this empirical relation, that is 4b plus 2.7 plus b plus 3.6 whole square, where b is the width of pile group, which we have calculated as n minus 1 into s plus d. We have calculated it as m minus 1 into s plus d, right? Either m you can use or n you can use. That is the number of pile either in a column or in a row, right? Now this particular formula, it is valid for the same load, per pile. Clear? It means when each and every pile it is subjected to same load, then only this particular formula will be valid. So it gives you what is the settlement of a group to the settlement of individual pile, which is given by 4b plus 2.7 upon b plus 3.6 whole square. I hope this particular concept is also clear. Right. One more topic which is added to your syllabus recently, that is lateral loading on the pile. That also we are going to discuss. So there is one more topic which is recently added in your syllabus, that is lateral loading on pile. Clear? So it may be expected that in upcoming GATE exams you may get the question from there also. Before that, there is one more important concept, that is of under-reamed pile. Now, in expensive soils like which are containing the Montmorillonite or like black cotton soil, right? So sometime what may happen, that your foundation can be subjected to upthrust. Your foundation can be subjected to upward load, or you can also assume it like that. Let's suppose this is the particular pile foundation below any windmill. So that windmill will be definitely in a particular location where the wind load is very high. So that wind load, it will try to pull out this particular foundation. So for such type of cases, what we do, we make one bulb in the dimension of this particular pile. We make this bulb in the dimension of this particular pile. Clear? We make the bulb in this dimension of pile. So this is particularly your bulb. We are calling it as bulb. Let's suppose this is having a diameter at du. The diameter of your pile is d. There is one relation between du and d. So your diameter of bulb, it is 2.5 times of this diameter of pile. 2.5 times of this diameter of pile. Now, how to calculate the load carrying capacity of these type of pile? That should be known to us, right? Now, for just analysis, I am taking a single bulb first. So what happens that when load is applied over this particular pile, the soil in this particular area will get compacted and it will act as a part of this particular pile. And it will act as a part of this pile. So you can take it a pile like this also. For the analysis, you can analyze this a pile like this. Here the width is, or diameter is du. Here the diameter is d. So you can say this is a pile having a diameter here du and this is d. Let's suppose this length is L1, this length is L2. For here also I can take, it is L1. You can analyze it like making this shape only. It will be easy for you to understand that. And L2, right? So the load carrying capacity due to this portion number 1, it will be different, and load carrying capacity due to this particular portion, it will be different, right? So here we will get the end bearing at this bottom, we will get the side friction here, we will also get the side friction here. Clear? So in case of clay soil, what will be the formula? Your load carrying capacity of pile, it will be 9C into AB, area at base. Now the area at base, as this soil is also acting as a part of pile, it means now you have to assume that this is the particular dimension of pile. So now the base at pile is du. Clear? So let's suppose this is the circular pile. So area will be what? Pi by 4 into du square. Pi by 4 into du square, right? Plus alpha into C bar into, for portion 1 first I am writing, into AS. What will be the AS value here? AS will be area at side, that will be the circumference multiplied by length, that is pi into d into L1, pi into d into L1, pi into d into L1. There will be more side friction from this. Plus, now try to understand, here now the interaction is between soil and soil. In this particular portion, most of the interaction is between soil and soil. It means again, here there will be no adhesion but cohesion. So it means here again alpha value for this case will be 1 into C bar into pi into, now base area is what? Base area is your du into L2. Clear? So there the formula is same formula, only you need to remember the concept that how, when alpha value will be 1 and which area you have to consider. And which area you have to consider. Examiner can give you 2 bulbs also. So in that case, this particular portion, it will act as a part of foundation. Right? This whole part will act as a part of foundation. Clear? So this will be the dimension at the this particular level and separately above. So you can calculate separately what will be the end bearing at this point and what will be the side friction for this particular portion and this particular portion. Clear? I hope this concept is also clear. There is one more concept of negative skin friction. There is one more concept of negative skin friction. Now, we have understood that the skin friction resistance, it is due to when pile is moving in the downward direction with respect to your soil. So when pile is moving in downward direction with respect to stationary soil, there was friction in this direction. And we have called it as skin friction. And this skin friction was responsible for increasing the load carrying capacity of your pile, right? But let's suppose there is a very loose soil surrounding to your particular pile. In that case, what will happen if let's suppose there is any surcharge load acting over this, or it may be due to different reasons. If this particular soil gets settled more than the pile material, if this soil gets settled more than this pile, what will happen? It means you can assume it like that, if relatively I will say what will be the movement of pile. if I take soil as a stationary, can I say that my pile is moving up as compared to this soil? If soil is moving with a higher speed in downward direction, if soil gets settled more than the pile, so what I can say? I can say, if I take this as a stationary, I can say that, okay, my pile is moving in upward direction. Here the pile was moving in downward direction, so friction was generated in upward direction. Here now, the soil is getting settled more as compared to your pile. It means now the friction will be generated in downward direction. Now the friction will be generated into downward direction. Let's suppose for this length L1, your soil gets settled more than your pile. It means here now the friction will be generated in this direction. It means this friction will be responsible to reduce the load carrying capacity of now this pile, right? For other portion, the friction is generated in upward direction only. So here, let's suppose the friction is generating in upward direction only, as here there is no settlement of this foundation. So in that case, how to calculate the load carrying capacity? The load carrying capacity will be calculated as, the only change will be what? Now there is a negative Aitken friction in L1 length. So let's suppose this is L1, this is L2. So what you can say? You can say, in case of, if I write for clay, it will be what? It will be 9C into AB, that is the end bearing resistance, plus this is 1, this is 2, right, plus, as this is negative in one portion number 1, I can write it as minus alpha C bar into AS. If I write the value of AS, it will be pi into D. I am assuming the pile to be having a circular base into L1, as it will be negative, right? Plus the side friction at this alpha C bar into pi into D into L2. Clear? So again, the formula is same. The only change is the concept that now this negative skin friction, as friction is in downward direction, so it will be responsible for decreasing the load carrying capacity. So you know that here this negative sign, it is used as for this negative friction. So it is decreasing the load carrying capacity of your soil. I hope this concept is also clear, right? How to write it for case of sand? So in case of sand, this end bearing resistance, there will be no change. So it will be what? It will be NQ into gamma into L into AB, plus there will be change in side friction. Now there will be change in side friction. What will be side friction? Side friction, we know it will be now minus half K gamma into L1 into AS1, area at side 1, plus, now try to understand. This half was for what? This was the average stress value up to this point. Average stress value was at this point. So it was 0 here, it was gamma into L1 here, right? Or if I talk about the horizontal stress, it will be K into gamma into L1 here. So you have taken the average of these two. For this particular soil, what will be the stress value? It will be this. So it will be K gamma L1 plus K gamma L2. Yes or no? Right? So now you have to take the average of these two values. For this particular soil. Clear? Plus this will become half, So it will be K gamma L1 plus half of K gamma L2 into sorry, here also there will be a friction factor into 10 delta into AS into 10 delta into AS. So this is the load carrying capacity in case of sand. This is the load carrying capacity in case of sand, right? So this is the case of your negative skin friction. One important case which we need to discuss is your pile under lateral loading. Your pile under lateral loading, right? So I have given you one example also. Let's suppose this is your pile below one windmill. Let's suppose this is the windmill, right? So there will be horizontal stresses or horizontal loading over this. So this is nothing but the lateral loading on the pile. If you take the effect of this at this point, what will be there? There will be one load value and one will be there moment value. Clear? This load and moment value will be here when this particular pile cap, it is fixed here. This moment value will be only when this pile cap is fixed. Clear? So there can be two cases: when the pile cap is fixed, when pile cap is free. So try to understand that this moment will be only when this particular portion will be fixed. Then only there will be generation of moment. Otherwise there will be only load. But for now I am assuming both the cases. So there is generation of load and generation of moment at this point. Now due to this generation of load and pile, your pile is going to get deformed. Your pile will have a deformation along the depth, right? And this is your deflection profile. Now try to understand this type of deflection profile. This type of deflection profile in which the deflection is 0 at the base of the pile. This is only valid for your long piles. This is only valid for your long piles. And to analyze the deflection in these long piles, there is one researcher known as Rees and Matlock. So these two scientists, Rees and Matlock, they have given one approach by which we can analyze this lateral loading over the pile, right? So try to understand this is only applicable for long pile. So whenever any question will come under the lateral loading of pile, first you have to check if pile is long pile or not. Now how to analyze that? For a long pile, the length of pile, it should be greater than 5 times the relative stiffness. This T is nothing but your relative stiffness. T is your relative stiffness. T is your relative stiffness. So if your length becomes greater than 5 times of T, you can say, okay, this is the case of long pile. And for long pile, for how to calculate this T value, this relative stiffness, you can calculate it using the formula as T is equal to 1 by 5 to the power of EI upon K. This EI is your stiffness value, right? This is I is your modulus of elasticity, E is your modulus of elasticity, and I is your moment of inertia, right? So EI will be your stiffness modulus, K, it is your modulus of subgrade reaction, and K is your modulus of subgrade reaction. So if these values are known to you, you can calculate this T value. If you compare this T value with length, if L will be greater than 5 times of this relative stiffness, you can say, okay, my pile is long pile. Clear? Now again, to calculate the deflection at different points, what we do? We use the superposition method. But we can say that this pile will get deformed due to this loading. So we'll calculate that what is the deformation due to this loading only, and what is the deformation in this pile due to this moment only. Once the individual deflection due to this moment and load is known to me, I can add those values and it will be equal to the combined effect of this load and moment, right? So here we are applying the superposition method, that what will be the load deflection due to this load, and separately we are calculating what is the deflection due to this moment, and by adding that we can get what is the total deflection. Clear? Now how to get this y1 and y2 value? Now this deflection at this point, it is the function of your load, it is the function of depth, it will be also the function of this T value, that is the stiffness of soil, that is the soil property, that is also equal to the pile material, that E value, that is nothing but the modulus of elasticity of pile material. It means it is also dependent upon the pile material, it also depends upon the geometry of material, that is I value. So after taking into account all these factors, here is the formula for calculating of deflection. So this y, it is equal to y1 plus y2, which is nothing but qg into t cube upon ei into ay. This ay is the deflection factor due to load plus mg t square ei into by. You can also remember it like that. If you remember that deflection in beam, how to remember this formula? I am just giving you one method. If you remember, due to any particular load, let's suppose it is having a length L. So if I say what will be the deflection at this point, you used to write that, okay, it will be WL cube upon 3ei. It was WL cube upon 3ei. Now try to remember this particular formula in this fashion. So this is your QG L. In case of L, take it as a stiffness factor upon ei, and that other units it is taken into account by ay. It is taken into account by this ay. Clear? Similarly, if I apply one moment, so we know that in case of moment, this one length dimension, it will decrease to 2. So it will be mg t square upon ei into by. These factors will be given to you by the examiner, right? These are your deflection factors. So this is your deflection factor for load, and this is the deflection factor for moment. In this same fashion, this particular total deflection formula is known to you. You can also remember the theta formula, that is slope value. We know that the slope will have one dimension less than this deflection value. So it will be qt square upon ei into this slope factor plus mg into t upon ei into this slope factor for moment, right? Similarly, if moment is asked, you know that moment will be what? Moment will be, we know that moment will be what? Moment will be your qg into t, one dimension less, divided by ei, right? So we know that it is theta divided by one dimension less divided by ei. So it will be qg into t into am plus mg into bm. Shear force also you can calculate, just remove one more dimension of t, you will get the shear force. You will get the shear force. So in that fashion you can just remember. Otherwise, there may be chances that you will get a question on this reflection, as this is the newly added topic. So there may be chances that you can get a question in this particular topic. So you can remember this particular formula. Also, I have told you that the moment will be there only when your pile head is fixed. So if your pile head is completely fixed, for that we have this particular formula of calculating the moment, that is minus 0.93 qg into t. Minus 0.93 into qg, that is the load into t. This load is at ground level into t. Clear? If the pile is free pile, so there will be no moment. If the pile is free pile, there will be no moment. You can take it as like, if you are having a fixed support, so definitely there will be generation of moment here, right? There will be a effect of moment here. But if this end is free, so due to this loading, or if this is hinge, due to this loading, there will be no moment here, right? So similarly, you can remember, when the pile head will be fixed, then only you will get this particular moment, otherwise it will be 0. Otherwise it will be 0. I hope this concept is also clear, right? Okay. Now, okay, also we can talk about how to calculate the settlement, right? There is one more point of calculation of settlement in pile. Settlement in foundation I'll take. If I talk about shallow foundation, we know that in shallow foundation there are only 3 formulas for the calculation of your settlement, and these formulas are also correlated, right? So whenever a particular data corresponding to different formula is given to you, you can use any of the formula. We know that the settlement upon thickness of compressible layer, it is equal to delta E, change in void ratio upon 1 plus E naught. So when this data is given to you, you can calculate from here. Also delta H is equal to H naught MV into delta sigma bar. Also delta S is equal to H naught Cc upon 1 plus E naught into log sigma naught bar plus delta sigma bar upon sigma naught bar. So these are 3 formulas. Let's suppose this is your particular foundation, right? Always remember, we are more concerned about the settlement of your clay layer, as we know that in sand the settlement will be completed within the construction period only. It means after the construction of our structure, the settlement of sand, it is not going to bother us. The effect will be mainly due to the settlement of your settlement of your clay layer, right? So we take into account the settlement of that clay layer only. So let's suppose this is the particular foundation and there is one clay layer here, and I need to calculate the settlement at this particular clay layer. So this is your clay. Let's suppose above this there is sand. Clear? So it means this is the particular compressible layer for me. This is the layer for which I need to calculate the settlement value. So thickness of this layer, we call it as H naught. That is the thickness of compressible layer, right? So H naught is known to me. Cc is your coefficient of compression, or compression index also we call it as. That is nothing but delta E upon log sigma 1 bar upon sigma naught bar, right? So effective stress sigma 1 bar upon sigma naught bar, and it is also the slope of your E versus log sigma bar curve, right? Now this change in effective stress, this effective stress, this effective stress, this effective stress, all are calculated at the center of compressible layer. So this is my compressible layer, it is its center. So all the stresses values are calculated at the center of this compressible layer. Now try to understand, there are 2 values, one is sigma naught bar, one is delta sigma bar. What is this sigma naught bar? This sigma naught bar is the stress or overburden pressure which was there at this particular level even before the construction of your foundation. When there was no foundation, when there was no superstructure, the stress value at this level will be due to the weight of the soil at this point. Will be due to the weight of the soil at this point. Yes or no? Let's suppose this soil is having a gamma value as gamma 1, having a thickness H1. This is your, if total thickness is H0, this is your H0 by 2. And let's suppose this clay layer is having a gamma value as gamma 2. So what will be my sigma naught bar? Sigma naught bar will be effective stress due to this soil, gamma 1 into H1, plus effective stress due to this soil, H0 by 2 into gamma 2. So this is your sigma naught bar value. It means this is the pressure value or stress value which was acting at this particular point even before the construction of our foundation. Now due to the construction of foundation, due to superstructure load, there will be change in stress value. That change in stress value is nothing but this sigma naught bar, this delta sigma bar. This delta sigma bar. How to calculate this delta sigma bar? This delta sigma bar will be equal to the load over this pile. Let's suppose that load is Q divided by area at the base of the area at the center of the compressible layer. load divided by area at center of compressible layer. Why we are calculating the area at center of compressible layer? As we want to find out what is the stress value at this particular point. Clear? Now, let's suppose the load is distributed as 1 vertical to n horizontal, right? Generally we take it as 1 vertical to 0.5 horizontal. If data is not given to you, you can assume it as 1 vertical to 0.5 horizontal. Clear? So if load is distributed in this particular fashion, what will be the dimension at this particular point? The dimension at this point will be, let's suppose the width of foundation is B. So this value, it will be B only, plus this extra dimension, that will be n into this distance up to the center of the compressible layer. Let's suppose it is Z from the base of the footing. So it is n into Z or n into Z. It means now you know the dimension at this center of compressible layer. Now you know the dimension at center of compressible layer. Clear? So by that you can calculate this delta sigma bar. This delta sigma bar will be Q divided by area at center of compressible layer. Area at center of compressible layer. Clear? So if these two values are known to you, you can calculate the settlement value. Also here delta sigma bar, you can use this particular, what is the change in effective stress? MB is your coefficient of volume compressibility, which is nothing but AV upon 1 plus E naught, or it is also change in volume with respect to initial volume when effective stress changes, right? Okay. Now if we talk about the settlement in pile, how to calculate the settlement in pile? Now there are two cases. Let's suppose first my pile is end bearing pile. My pile is end bearing pile. So when the pile is end bearing pile, the analysis will be same as your shallow foundation. Let's suppose this is the pile, right? So what we do, we assume a raft at this point. It means we will assume that the load will be distributed from this particular point. Load will be distributed from this particular point, right? Let's suppose this is the compressible layer. Let's suppose this is the compressible layer. So load is distributed, let's suppose in this fashion. We will calculate the sigma naught bar value, delta sigma bar value at this particular center of the compressible layer. This is H naught, this is the center of compressible layer. So we will calculate sigma naught bar value, we will calculate delta sigma bar value at this point, and we can use delta H is equal to H naught Cc upon 1 plus E naught log sigma naught bar plus delta sigma bar upon sigma naught bar. Clear this thing? It will be same. Here the load will be distributed from this base, as there will be only end bearing. There is only end bearing. Like our shallow foundation, in our shallow foundation also, there will be no side friction, right? There is no side friction as the depth is very less. So it means this is the case similar to the shallow foundation. So similarly, you can calculate the what will be the settlement value. Clear? So try to remember that the load distribution we take into account from this, from the base of the foundation. From the base of the foundation. Clear? Now, if this is the friction pile, what will be the change? In case of friction pile, if it is a friction pile, so we know that some of the load, it will also get distributed due to the side friction from the sides. It means total load is not getting distributed from base of the footing. It means total load is not getting distributed from the base of the footing. So what we do, we assume that this load is getting distributed from a depth 2/3 times of L from the top. If the length of the foundation is L, this is the ground level. So what we assume, that the load is getting distributed from the 2/3 times of L. As we know that along the length there will be distribution of load. From the base also there will be distribution of load. So you cannot take now that the whole load is getting distributed from the base. So what we do, we take a particular depth, as we know that from the top there will be less distribution of load, from the bottom there will be more distribution of load. So what we do, we take a raft, or we assume an imaginary raft at a distance 2/3 times of length of the pile from the top, and we assume that from here the load is getting distributed. From here the load is getting distributed. So again the process will be same. The only concept is now you have to distribute the load from this 2/3 times of L, right? This value is what? This value is your 1 vertical to n horizontal. Again, I have told you that if these values are not given to you, you can take it as 1 vertical to 0.5 horizontal. Clear? Or it can also be written it as 2 vertical to 1 horizontal. Both are the same case. 2 vertical to 1 horizontal. I hope this concept is also clear. After that, we have having a concept of soil exploration. So in soil exploration, you should know that what are the different types of samples. So we generally use two types of sample. One is undisturbed soil sample and one is representative sample. Clear? So what is the undisturbed sample? In undisturbed sample, your mineral composition and structure of soil. Structure of soil is conserved, right? It means there is no change in structure of the soil, there is no change in mineral composition while taking the sampling of the soil. So you can say, okay, this particular soil is undisturbed soil sample. When you can say undisturbed soil sample, if the mineral properties are not going to change, if the structure of soil is preserved. Clear? So you can see that. Also you can say that mineral composition means particle size distribution is not changed, also as well as structure is also remains preserved, right? So you'll call it as undisturbed. Whereas if in a sample having same particle size distribution, but there is a slight change or partial change in the structure of sample get partially disturbed. If it means this is what, if mineral composition it is preserved but there is slight change in structure. So you will say there is slight change in structure. So what you will say, it is a representative sample. Whereas in disturbed sample, if this mineral composition also get changed, you will call it as disturbed sample. So generally we use undisturbed sample like for the calculation of shear strength, for consolidation test, right? Whereas representative sample can also be used, as it is very difficult to get always this undisturbed sample. This can be used for Atterberg limits, that is, you know that liquid limit, plastic limit and shrinkage limit. Also for the calculation of specific gravity. Clear? Compaction test. So for all these you can compromise with a slight change in the structure. Clear? Next important thing from which examiner can ask you the question is the characteristics of the sampler. So this is the sampler which is having one cutting edge. So this is the side view of a sampler, right? So this is having a cutting edge. You will just insert this cutting edge into ground. This will cut a sample and you will get a sample in this particular tube. So this is your sample tube, right? Here you got a sample. So this is your sample tube. This is your cutting edge. So always remember this diagram as like this. So this is your cutting edge. This is your sample tube. This is your sample tube. Clear? Now, there should be these dimensions. Let's suppose this is your dimension D1. If I say this is the dimension D1, that is the internal diameter of this cutting edge. D2 is the outer diameter of cutting edge. Similarly, D3, it is the internal diameter of your sampler, and D4 is the internal diameter of this sample tube, right? Now, these dimensions should be such that your sample, it will be undisturbed or representative, right? So your sample will be undisturbed or representative. It depends upon, or how much disturbance will be there in your sample. It depends upon the dimension of these. Clear? So for that we have some ratios. One is your inside ratio, or we call it as inside clearance. So there are some formulas from where you can get the numerical. First characteristic is inside clearance. What is inside clearance? Inside clearance, it is the difference of your inside diameters. Now inside diameter of what? Inside diameter of sampler, inside diameter of sample tube, and inside diameter of this cutting edge. Now I try to understand. This value is higher, this value will be less, this value is higher, this value is less. It means to calculate this inside clearance, I have to subtract this D1 value from this D3. This D1 value from D3. It will give you, okay, how much is the clearance, inside clearance for my sample. The difference of these two is how much is the inside clearance for my sample. If after coming a sample here, it may expand to some extent, right? So that there should be some clearance, so that there will be no further stresses over that. And this clearance should not be as much high as this particular sample. It will get so much space that it will get completely disturbed, right? So for that we have one ratio, that is inside clearance. So it will be D3 minus D1 with respect to this D1. Clear? So it is inside clearance, that is Ci, that is D3 minus D1 upon this last one, D1 into 100. Clear? Its value for a good sample should be in between 0 to 2%. Should be in between 0 to 2%, right? Second is your outside clearance. Outside clearance. Outside clearance is the difference between the outside diameters. Difference between the outside diameters. Now try to understand. Here the outside diameter of cutting edge is greater than outside diameter of this sample tube. It means the difference I have to take is D2 minus D4. That is D2 minus D4 divided by this last value, D4. So it is C outside, it is D2 minus D4 by D4 into 100. Clear? For a good sample, this value should be in between 1 and 3. 1 and 3%. There is another term which we call it as area ratio. Which we call it as area ratio, AR. So this AR, it is the difference of square of dimension of your cutting edge. So in area ratio there will be difference of your cutting edges, right? So it is D2 is greater than D1. So I can take it as D2 ka square minus D1 square divided by D1 square into 100. So that is your area ratio. That is area ratio. Again, for good sample, you can remember that this area ratio should be less than or should not be greater than 10%. This area ratio should be less than 10%. If this value is less than 10%, you can say, okay, my sample is a good sample. This is the value for your outside clearance. If this value lies in between this, you will say, okay, I'll get a good sample. Similarly, if inside clearance is in between 0 to 2, you will say, okay, this sampler will give me a good sample value. Clear? Now, last part is my stability of slopes. Last part is my stability of slopes. Now try to understand what are the different formulas in your stability of slopes. We define stability of slopes into two categories. So if we talk about slope, it is your infinite slope and finite slope, right? Infinite slope and finite slope. And finite slope. We know that if the soil properties are same for a greater extent, we can say that is the infinite slope. If the soil properties are homogeneous for a greater length, you will say, okay, that particular soil is that particular slope is infinite slope. And we know in infinite slopes, generally we will find out that the failure will be a planar failure. So let's suppose this is your slope and this is your failure plane. This is your failure plane. This is your slope face. This is your slope face. So in infinite slope, you will find out that the failure is your planar failure, right? So linear failure you are getting. Whereas if we talk about the finite slope, in finite slope, those are having a finite extent. It means it is having a fixed point from it where it is starting and where it is getting end. Also, the properties of soil within this particular length may change, right? In this particular type of foundation, we will find out that in this particular type of slope, we will find out that the slope get fail as a spiral or circular failure, right? So there can be different type of failure. This part we call it as a face of slope. This point we call it as a toe of slope, and this is your base of slope. Clear? If the face of slope get failed, we call it as a face failure. We call it as a face failure. So here you can see, for this particular case, your face is getting failed, so it will be your face failure. If your failure plane passes through the toe, it will be a toe failure. And if failure plane passing through the base of this particular slope, you will call it as a base failure. Clear? If the strength of soil above the toe, it is less as compared to the strength of soil below this particular toe, so what will happen? This face failure will be there. Clear? In case of base failure, if the soil is having same strength above and below, and soil is steep, you will find out that there will be toe failure. Also there is one observation that if let's suppose this slope angle is beta, if this beta is greater than 53 degree, irrespective of the phi value, always you will find out that the slope will get fail along this toe. Clear? So you can also remember this. Whereas if this particular slope, it is flat or more or less flat, and the strength of soil below the base or below this toe, it is weak, or the soil below this soil below this base, it is weak as compared to the soil above this base or above this toe, you can say that your failure will be base failure. Clear this thing? Now, in this particular chapter, examiner mainly asks you for the calculation of factor of safety. So first we will see the different cases in your infinite slope. infinite slope. What is my factor of safety formula? Factor of safety, it is the ratio of resistance against failure upon the resistance which is causing the failure, right? So we know that the shear strength of soil, it is responsible for the resistance against failure, which is given by C plus gamma into Z cos square beta into tan phi. And this shear stress, it is gamma into Z sin beta into gamma into Z into sin beta. Clear? Or we can just derive that particular relation also. Let's suppose this is your particular slope, right? And this is your failure plane. If I assume one element, this is your failure plane, this is your slope face. This is your failure plane. Let's suppose this dimension is your B. This angle of slope, it is beta, right? So I can say that it is your B cos beta, right? There will be weight over this particular wedge, that is W. It will have two components, that is W sin beta and W cos beta. Clear? So from there we have written that this particular W sin beta, it will be responsible for the shear stress value, right, or destabilizing force value, whereas the friction at this point, it will be your stabilizing force, and this friction will be nothing but equal to tan phi into this normal. These are the values of forces. We can take the values of stresses, so it will be gamma into Z into cos beta into sin beta, right? Now we take the different type of cases for first cohesionless case, for cohesionless soil. So if it is a cohesionless soil, it means C value is equal to 0. In this, first I am taking a case of when the soil is either dry, either submerged, either in bulk condition. If these are the cases, what will be my factor of safety value? Factor of safety will be, if soil is dry, this will be gamma dry into Z. This will be gamma dry into Z. It means these values will get cancelled out. Cos beta will cancel out. It will be cos beta upon sin beta, or I can say it is sin beta upon cos beta, which is nothing but tan beta. So I can say that factor of safety will be tan phi by tan beta. Factor of safety will be tan phi by tan beta. So if soil is given you dry, submerged or bulk, you will say, okay, my factor of safety will be tan phi by tan beta in all the cases. Second case is case of seepage. Second case is case of seepage. When there is a seepage. So let's suppose this is your soil, this is your face of the slope, this is the ground level, this is the water table, and this is your failure plane, and this is your failure plane. All are parallels, right? I'll just draw it so that it will look like a parallel line. Clear? So this is your failure plane. This is your water table. This is your ground surface. or face of your slope. This is your face of slope. Clear? Now, if this is the water table, let's suppose water table it is at a height h from here, and this is your z value. Clear? So, okay. So, in this case, try to understand, always your strength in the soil, it will be due to effective stress. Always remember this concept that in your soil, your stress will be due to what? Your stress. Shear stress, it will be due to the total weight of soil, whereas your strength in soil, it will be due to effective stresses, right? So, we know that factor of safety is nothing but shear strength of soil upon shear stress. Factor of safety is what? Shear strength of soil or of the slope versus shear stresses, right? So, now I need to calculate the shear strength. If I calculate the shear strength, what will be the formula? It will be gamma. Let's suppose this soil is having gamma as gamma bulk, so it will be gamma bulk into z minus h plus this soil weight, that is gamma submerged into h, gamma submerged into h. This is the average gamma value into cos square beta into tan phi divided by, when we are taking the weight of this soil, we have to take it as saturated, as total weight. So, it will be what? It will be gamma bulk into this z minus h plus gamma saturated into h into cos beta into tan phi, cos beta into sin beta, right? Cos beta into sin beta, right? So, it will be your particular formula. You can also modify it. If I just divide it with this particular value, what we can get? If I take this particular value, gamma bulk into gamma z into h plus gamma submerged into h as common. So, this particular value will also get common. Here we will get one value, here we will left with gamma submerged, and here we will get with gamma w, right? So, we can also modify it in terms of gamma average. Also, what you can do, you can also take this particular soil as, you can calculate the gamma for this particular soil as gamma average, right? When you are calculating that gamma average value, first take this soil as saturated soil, as we have to use the saturated soil weight in this particular denominator. So, what I can do, I can use that saturated value, I can calculate the gamma average based on this soil, considering this soil to be saturated, and to use that particular average gamma, I can just subtract the weight of water in the denominator, in the numerator, right? So, also what we can do, we can also take it as like this. If I calculate the gamma average value, so what will be gamma average? It will be, let's suppose this soil is having gamma as gamma bulk, and I am assuming, although this is in submerged condition, but we know that its weight, which is causing the shear stress, it will be due to the total weight. So I am considering it to be saturated for now, right? So it will be gamma bulk into this Z minus H plus gamma saturated into H divided by total heft, that is Z. Now how you can write out this particular formula for factor of safety? Now you can write the factor of safety as factor of safety is equal to effective stress. It will be responsible for strength. So in numerator there is strength. So it will be gamma average into H, as now total soil is having the gamma average value. So gamma average into Z. Gamma average into Z. It will be gamma average into Z. From it, as this gamma average I have calculated taking the soil to be saturated, taking the soil below water table to be saturated. So what I can do? I can just subtract gamma W into H from here. Now it will be the effective stress into cos square beta into tan phi, right? Whereas writing the shear stress value, I can directly take it as average, as this is taking into account the saturated soil, into Z cos beta into sin beta, cos beta into sin beta, right? So you might have remembered this particular formula in this fashion. If I divide this, it will be what? It will be 1 minus gamma W into H upon gamma average into Z, and it will be what? It will be tan phi by tan beta. Clear? So like this also we can remember this formula, factor of safety, or directly you can write the stress values while taking the shear strength, write the effective stress value, while taking the shear stress, take the total stress value, right? Or although you can remember this particular formula. In this case, if our seepage will be at ground level, so its special case will be seepage at ground level. So what if seepage is at ground level? It means my H value is equal to Z. So if I put just H is equal to Z, it will be what? Factor of safety will be gamma submerged upon gamma saturated into tan phi by tan beta. Factor of safety will be gamma submerged upon gamma saturated into tan phi by tan beta, right? So you can also remember this particular formula. Next, this is the analysis of your infinite slope. If I talk about the finite slopes, right? So in finite slope, you need to remember only that one method, which is your Swedish slip circle method. Right, let's suppose this is the finite slope, and in this the failure is in the form of a circular arc. Definitely this circle will have some radius, or I'll draw it here. Let's suppose this is your infinite slope. Sorry, this is your finite slope, and this is the failure plane. This is your failure plane. Let's suppose this failure plane, it is an arc of circle. So definitely there will be some center. Let's assume the circle is having a radius r. Clear? Now try to understand this particular wedge of soil, if it is having a weight W, this weight either examiner can give you or examiner can give you the unit weight of this soil. If you will multiply this with volume, as we know that gamma is equal to weight by volume, so we can say that weight is equal to gamma into volume. So from here also you can calculate, right? So there can be these two cases. Now this particular wedge, it will slide in this particular direction. It will have a tendency to slide or get failed in this particular direction. This will be due to this weight component. As this is sliding about this particular point, it means we have to consider the moment value. We have to consider the moment value. So let's suppose the line of action or the lever arm of this weight from this particular center, it is x bar. So what will be the moment of this weight W about this center? It will be W into x bar. This particular moment, it trying to fail this particular wedge, whereas there will be another force that is due to the cohesion between the particles at this point. Cohesion between the particles at this particular point. Let's suppose the cohesion value is C. So what will be the cohesive force? So cohesive force will be C into area at which it is acting. Let's suppose if I take the dimension along or inside this particular screen to be 1. So area will be 1 into the length of this particular arc, right? So it will be C into L. What will be the length of arc? Let's suppose this sector is having an angle theta. We know that the total circle, it will have a length of 2 pi r when my theta is equal to 360 degree. As here the angle is theta, so what will be the value? It will be 2 pi r by 360 degree into theta. So this will be my length, right? And this cohesive force, it will create a moment of CF into R about this particular center. So what will be my factor of safety? My factor of safety will be the stabilizing moment. Stabilizing moment is what? That is C into L into this R value divided by the destabilizing moment, that is W into x bar. That is W into x bar. I hope this concept is clear, right? So this is all about this particular session. We have discussed all the important topics related to your foundation engineering. We have discussed the shallow foundation, we have discussed deep foundation, that is pile foundation. We have discussed about the soil exploration, and we have also discussed about this stability of slopes. All the other important points related to your geotechnical engineering was already covered by Sandeep Adari sir. So you can also watch that particular video. It is available on YouTube. So by then, now you should focus on your revision, right? So try to revise all the concepts, try to give the test series. This is the particular time when you should start giving the test series. You should analyze those test series and keep on revising those concepts which you have already done. It is not the time to read the other topics, right? Whatever you have studied throughout the year, now try to sharp all those particular concepts, and good luck from my side. Good luck for your exam.